Today, we are going to talk about something very important in the world of data. It's called the relational model and the systems we use to manage it, which we call RDBMS. First, we will learn about relational model concepts. This is the big idea. We will break this down into three parts. Structure. How do we organize the data? What does it look like? Constraints. What are the rules we must follow to keep our data good and correct? Operations. What can we do with our data? How can we add it, change it, or remove it? After we understand the idea, we will look at the tool. The tool is the Relational Database Management System, or RDBMS. This is the software we use. And finally, we will see the language we use to talk to the database. This is called SQL, or Structured Query Language. In the past, we had different models. The first ones, like the hierarchical and network models in the 1960s, were a bit difficult to use. They had very strict rules. Then, in 1970, Edgar Codd introduced the relational model. It organized data in simple tables, like a spreadsheet in Excel. It was very flexible, and it became the most popular model in the world. Later, other models came along, like object-oriented models, and more recently, NoSQL, for big data. Let's begin with our first topic, relational model concepts. So, we are now diving into the core ideas of the relational model. The relational model was proposed by E.F. Codd, and the main idea is this. We store data in tables. The official name for a table is a relation. In the relational model, we use special words for these. The columns are called attributes. The rows are called tuples. Each row is one complete record or piece of information. The best thing about this model is its simplicity. It's very easy to understand, and it hides all the complex computer details from us. Let's look at this picture to make it super clear. Here we have a table, or a relation, called products. You can see the whole thing is the table. The titles at the top of the columns, products key, description, brand, price, these are the attributes. They are the properties that describe our products. And each row, like the first row for watch or the second row for shoe, is a record or a tuple. It's one single item in our database. Now that we know the basic parts, let's learn the formal way, the official way to describe the structure of these tables. When we want to describe the design of a table, we use a special notation. We write it like this. Let's break that down. R is the name of the relation or the table. For example, student. Inside the parentheses, we list all the attributes or the columns. Name, SSN, home phone, and so on. So student, name, SSN is called the relation schema. Think of the schema as the blueprint or the plan for the table. It tells us what the table looks like, but it doesn't contain the actual data. When we just say student, we usually mean the table with all the data inside it right now. The schema is the design. The relation is the table with the data. Now, what happens if we have two different tables and both tables have a column named name? For example, we could have a student table with a name column and a professor table that also has a name column. If we just say name, how does the computer know which one we mean? To solve this, we can use a dot notation like this. Student.name. This is very clear. It means the name attribute that belongs to the student table. We also have a special way to talk about the data in the rows, or tuples. A single row is called T. So T could be the row for Barbara Benson. If we want to get the value from a specific column in that row, we can write T, attribute name. For example, T, age, would give us the value of 19 from Barbara's row. We can also get multiple values at once. If we write T, name, age, we would get Barbara Benson and 19. This is just the formal mathematical way to write it. It's a precise way to say, for this row, give me the data from this column. Okay, quick review. Let's look at our student table. We call the whole table that a relation. We call the plan for the table that the relation schema. We call one column, like age or GPA, an attribute. And we call one row, like the information, that a tuple. And if T is the row for Rohan, the T name be Rohan Panchal. Let's look at one more clear example. Let's say T is the second tuple, the row for Barbara Benson. So T is the entire set of values. If we write T name, we get just her name, Barbara Benson. If we write T, SSN, GPA, age, we would get a small collection of her data. This notation is the basic language for working with data in the relational model. Okay, we know what tables look like, but relational tables have some special rules or characteristics. Let's learn about them. Here are the most important rules for relational tables. First, the order of rows is not important. It doesn't matter if it is the first row or the last row, its information is still the same. The database can store the rows in any order it wants. Second, each value in a row must be atomic. Atomic means it cannot be broken down into smaller parts. For example, in the age column, we have the value 25. We don't have 25 years and 2 months, just one single value. If you have an attribute like name, you should break it into first name and last name to make it atomic. This is a very important rule called the first normal form. We will study that more later. Okay, what about null values? Look at the home phone for Dick Davidson or the office phone for Barbara Benson. The value is null. What does null mean? It's very important. Null does not mean zero. It does not mean an empty space. Null means the value is unknown or not applicable. For example, maybe Barbara Benson doesn't have an office phone, so the value is not applicable for her. Or maybe we just don't know Dick Davidson's home phone number. The value is unknown. Null lets us represent this missing information. Finally, the meaning of a table. You can think of each row as a single complete fact. The first row is a fact about a student named Dick Davidson. The second row is a fact about Barbara Benson. The whole table is a collection of facts about students. Okay, we have finished structure. Now we move to our second big topic, constraints. Constraints are rules. Rules are very important to make sure our data is correct and has high quality. Let's see what these rules are. So, what is a constraint? A constraint is a restriction or rule for the values in our database. Why do we need rules? We need them to protect our data. We want to make sure the data is valid and makes sense in the real world. Think about a game like football. There is a rule that you cannot use your hands to touch the ball, unless you are the goalkeeper. This rule makes the game work correctly. Database constraints are just like that. They are rules to make sure our data is played correctly. We can put these rules into three main groups. Inherent or implicit constraints. These are the automatic rules of the relational model itself. For example, a rule that you cannot have two rows that are exactly the same. You don't need to create this rule, it's part of the system. Schema-based or explicit constraints. These are rules that we define when we design our table schema. For example, we can say that the age column must be a number, or we can say that every student must have a student ID number. We explicitly write these rules. Application-based or business rules. These are rules from the real world that are more complex. For example, a university rule might be, a student cannot register from more than 7 classes in one semester. The database itself doesn't know this rule. The application program, like the university website, must check this rule before it adds data to the database.
Let's look at the first type of rule we can create, the domain constraint. A domain is the set of all possible legal values for an attribute. For example, for the age attribute, the data type is number. But we can be more specific. The domain might be integers from 16 to 100. A value of 5 would be the wrong data type if it was text, and outside the domain if it was a number. A value of 200 is the correct data type, but it is outside our domain. So, a domain constraint makes sure that any value we put in a column is of the correct type and is within a legal range of values.
This is one of the most important concepts, key constraints. Keys are used to find one specific row in a table. Every attribute has some predefined value and scope, which is known as attribute domain. A candidate key is an attribute, or a set of attributes, that can uniquely identify one row. For a student, their national ID number could be a candidate key. Their student ID number could also be a candidate key. Both of them are unique for each student. They are candidates to be the main key. So the primary key is the one candidate key that we choose to be the main identifier for the table. So the primary key is our main tool to guarantee that every row is unique and we can find it easily. Foreign key constraint is how we connect our tables together. Look at the two tables here. We have products and we have brands. In the brands table, brand ID is the primary key. It uniquely identifies each brand. Now look at the products table. It also has a brand ID column. This brand ID in the products table is a foreign key. A foreign key is a column in one table that refers to the primary key in another table. It creates a link, a reference. This rule, called referential integrity, says that any value you put in the brand ID column of the products table must already exist in the brand ID column of the brands table. It prevents you from adding a product with brand ID of 5 if there is no brand 5 in your brands table. It keeps the data consistent across tables. It's how we build relationships. We talked about null values. Sometimes we want to make a rule about them. We can set a constraint called not null. For example, for every student, we must have their name and their student ID. It makes no sense to have a student with no name. So when we design the table, we tell the database that the name attribute and the SSN attribute are not null. If someone tries to add a new student but leaves the name empty, null, the database will reject it. It will say, sorry, you're breaking the not null rule. For other attributes, like home phone, we can't allow nulls because it's okay if we don't know a student's home phone. We have now covered structure and constraints. The last part of our concepts section is operations. Operations are the actions we can perform on our data. What can we do with our tables? There are three basic operations. The first one is insert. Insert simply means adding a new row or tuple to a table. For example, if a new student joins the university, we insert a new row for them in the student table with all their information. But what happens when we insert? The database is very careful. It checks to make sure the new data does not violate any of our constraints. Does the age have the correct data type? Domain constraint. Is the new student ID unique? Primary key constraint. Is the name not null? Null value constraint. If any rule is violated, the database will reject the insertion and give an error. The second operation is delete, which means to remove a row from a table. Deleting can sometimes be tricky. If we delete a student, that's usually okay. But what if we try to delete a brand from our brands table, and there are still products in the products table that refer to that brand? This would violate our foreign key rule, or referential integrity. We have three options for what can happen. Restrict. This is the default. The database says, no, you cannot delete this brand because other tables are still using it. The deletion is rejected. Cascade means delete them too. If we delete the Nike brand, the database will automatically go to the products table and delete all the products that are made by Nike. Be careful with this one. Or set null. If we delete the Nike brand, the database will go to the products table and change the brand ID for all Nike products to null. This means we don't know the brand anymore. And the third operation is update, which means to modify or change data that is already in a table. For example, a student changes their phone number. We use update to change that value. Usually, this is simple. The database just checks if the new value follows the domain constraint. For example, the phone number is in the correct format. But if you try to update a primary key or a foreign key, it can be complicated. If you change a student's ID number, you might have to update it in many other tables that refer to that student. It has the same issues as insert and delete. We learned about the three key concepts of the relational model. Structure, data is in tables, which are relations, which have columns, or attributes, and rows, or tuples. Constraints, these are rules to protect our data, like domain, key, foreign key, and null constraints. And operations, these are the basic actions we can do. Insert or add, delete or remove, and update or change. These three ideas are the foundation of everything. Now that we understand the theory, let's talk about the real software we use. This is called a Relational Database Management System, or RDBMS. On the left, you have your raw data, maybe in files. This is just information. In the middle, you organize that data into a relational database. You design the tables, the columns, the rows, and the relationships, just like we learned. But how do you manage it all? How do you enforce the rules? How do you let people use it? For that, you need the software on the right. the RDBMS. The RDBMS is the engine, or the manager. It's the program that does all the work. It stores the data, enforces the constraints, and lets us perform operations. Examples of RDBMS software are MySQL, Oracle, and SQL Server. So why does everyone use an RDBMS? Because they have many advantages. Data structure. The table format is very simple and easy for people to understand. Maintenance. RDBMS software comes with tools to help you maintain the database. You can easily test it, repair it, and, very importantly, back it up so you don't lose your data. Network access. You can put your database on a server computer, and people can access it from their own computers over a network or the internet. This is how websites and apps work. Here are more advantages. Multi-user access. This is a big one. An RDBMS allows many users to access and change the database at the same time. It has special systems to lock data so that two people don't try to change the exact same thing at the exact same moment and cause a problem. Privileges. You can control who gets to see and do what. A database administrator can set up rules. For example, a manager can see employee salaries, but a regular employee cannot see the salaries of their colleagues. This is very important for security.
Language. Almost all RDBMSs use the same standard language, SQL. Once you learn SQL, you can work with many different database systems.
And finally, here are some of the most popular RDBMS software in the world today. You have probably seen some of these logos. MySQL is extremely popular, especially for websites and web applications. It's free and open source. PostgreSQL is also open source and is known for being very powerful and having many advanced features. Microsoft SQL Server and Oracle Database are very popular in large companies and corporations. And SQLite is a very small, lightweight database that is often built directly into mobile phone apps and small programs. Your smartphone probably uses SQLite for many things. They are all based on the same relational model concepts that we learned today.